Okay, so particle kinetics number 7. Okay, so this motorcycle is going through a circular path, and we're talking about right up at the top. And let's see, the radius is 2 meters. The speed is 15 meters per second. The motorcycle and the rider together is 350 kilograms. Okay, so we want to calculate first the total acceleration and then some force stuff. This is circular motion. So I'm going to put the origin of the coordinate system right at the center and use these directions. The velocity vector, if it's going the way I showed with that arrow, the velocity vector has to be tangent to the circle in that direction, so 15 meters per second. That's the velocity. The speed isn't changing, so there's no tangential part of the acceleration. It is changing direction, so we know that there's a centripetal acceleration like that. And the magnitude of the centripetal acceleration is v squared over r, which is 225 over 2, so 112.5 meters per second squared. Excuse me. And that's pointing in the negative y direction. So the centripetal acceleration as a vector is 0, negative 112.5. And that's the total acceleration because there's no tangential. So that's part A. And the units are meters per second squared. Any questions about that? Yeah, because the only other possible acceleration is the tangential part. And the speed isn't changing, so there's no tangential part. Centripetal just means towards the center. So no, it's not its own kind of force. The way you figure out the force is acting on something is you know that weight is acting, and then you just look for contact, and then you treat each individual contact as a separate thing based on whether it's pushing, pulling, you know what I mean? But there are some forces that are centripetal, that's like in this case, it's a normal force, but that normal force is going to point towards the center, so you could call it a centripetal force. In this case, yes, that's right. But we haven't dealt with any forces yet. All we did so far was use what we know about circular motion. Not yet, but I guess for part C we'll do that. For part B, you guys remember the thing? Remember what you can do in all the rest of your classes if you're silent right now? Remember? You can talk all day in every other class. Let me know if you need a note. Okay, so Newton's second law, to calculate a net force, you don't need a free body diagram for that. You just multiply the mass times the total acceleration. So for this one, F net, we will do a free body diagram for part C. But F net is equal to 350 times 0, negative 112.5. What's 350 times 112.5? Okay, so 0, negative 39,000? Wow, that's a lot. Well, that's a heavy motorcycle, and it has a lot of acceleration because I made the radius really, really small on that circle. Okay, so that's the net force. Still, we haven't broken it up into individual forces. So now we'll do the free body diagram for C, and we'll think about the individual forces. Because now we don't just want the net force, we want to figure out what's the part of the net force that's made up of the contact with the circle. What? In C. Okay. Yeah. By the path. So that's the contact force. Okay, so let me just finish anyways since I'm already here. Okay, so that's an upside down motorcycle. The normal force is perpendicular to the surface, perpendicular to the surface toward the chosen body. So that's this direction, okay? It's a pushing contact. And then there's also the weight, like you said, that in this case happens to be in the exact same direction. That's 350 times 9.81. What's that? Someone calculate that. What? That's it, yes. Okay. And now Newton's second law. So now we can calculate those individual things. We have 0, negative n, plus 0, negative 33.5 is equal to the mass times acceleration, which is the net force we already calculated. And so what do you get when it's going to be 35 something, negative 35 something. Okay, so n is positive. Okay, n is just a variable, and you just do the algebra, and it gives you that n is positive. So you should always, for that variable, you should always get a positive number. Well, yeah, n is just this variable that we're solving for, but the vector is this whole thing, which is the force on the motorcycle by the ramp or whatever. Okay. That is a vector. So to solve for that normal force variable, you just get the positive number. If you wanted the force vector on the motorcycle by the ramp, you take that variable, plug it back into the vector, and you get 0, negative 35,941.5. Yeah, that's right. Any other homework questions? Yes. Energy. Okay. Okay, so for a pendulum, we want an equation that relates the speed to that current angle, and we're assuming the length is L. Okay, so we have this mass m. That's going to disappear from this calculation. We're assuming that there's a angle theta at this instant, and the length of this string is L. And we want a relationship between the speed and the angle. Let's see. All right, well, if you set this up as a right triangle, the length on this side, you know, the horizontal distance is L times the sine of theta. And this length is L times the cosine of theta. And the fact that we're relating a position variable to a speed variable suggests that energy is the way to do this. Also, the fact that this problem is on a set of problems that says energy at the top is a good giveaway, but you know, like on a final or an AP test or whatever, you don't have that. So you need to recognize the fact that this is relating an angular position to speed, and so we probably want to use energy. And it's released from rest at an angle that's a capital theta. So at rest, this angle is this capital theta. And so we can set up, well, first let's do the free body diagram and make sure that we can use that conservation of mechanical energy. What's required so we can use the conservation of mechanical energy? Yes. Well, yes, that is the right idea. Technically, you can have non-conservative forces, and we will here, as long as they don't do any work. Right. Yes. Perfect. Okay, so we have a weight force, mg, and we have a centripetal force, T. Conservative forces, we have the weight. Non-conservative, we have that tension, but it doesn't do work. So we know we can use conservation of mechanical energy. So let's set it up. We have an instant 1 and an instant 2. And we just have to do the potential and kinetic energy. At instant 1, the potential energy. First thing we have to do is choose a zero height. So I guess the easiest thing for zero height would be to put it here. That's going to make all the potential energies negative, but that's not a problem because all that matters is the change in potential energy. Okay, so if this is h equals 0, then at rest, so instant 1 is when this pendulum is at rest. When theta is equal to this constant capital theta, what's an expression for the potential energy? Well, what we want is the height. And so that's the right idea. So it's going to be, and remember, we want, that height has to get bigger as you go up for potential energy to work. And so if our height is equal to 0 at the ceiling, this has to be negative L cosine capital theta. Who's with me on that? Who's not with me on that? Kinetic energy is always positive. Potential energy can be negative because you can choose your 0 height anywhere you want. You know, if you chose your 0 height to be at 30,000 feet, then everything that happens on the surface of the Earth would have a negative potential energy. But it doesn't matter though, because even if the potential energy is negative for everything in your problem, all that matters is that change in potential energy, and that would still be positive if the thing is going up and negative if the thing is going down, just like, you know. So yeah, potential energy can be negative or positive. It just depends on where you choose your 0 height. Question? No, it says in the problem, at rest, this angle theta is the constant capital theta. So it's pulled out. This is too long. It's pulled up to a position like this and then let go. In this position, the angle there would be capital theta. It's at rest at the instant you release it. And then it speeds up as it goes down and slows down as it goes up. Okay, so potential energy is negative L cosine capital theta. Could everyone here reproduce that thought process? And then what's the kinetic energy at the instant it's released? 0, because it's at rest. And at instant 2, what's the potential energy? Perfect. And what's the kinetic energy? 1/2 mv squared. You're owning this. Good job, Christo. Peaking right at the right time. Okay, so then conservation of mechanical energy says negative L cosine capital theta plus 0 is equal to negative L cosine lowercase theta plus 1/2 mv squared. Oh, you might be confused about how I'm writing this because this is just the height. There's stuff in the potential energy. So this should be negative mgl cosine capital theta. And the other one should be negative mgl cosine lowercase theta. Okay, negative mgl Okay. Well, now we can cancel out the m's, multiply everything by 2, and you get negative 2gl cosine capital theta plus 2gl cosine of lowercase theta is equal to v squared So V is equal to plus or minus square root of 2GL times the quantity cosine of lowercase theta minus cosine of capital theta. That's all square root. This V that we're trying to find is a speed, so we want the positive answer for this always. What do you get if, what happens if that cosine of lowercase theta, what do you get if that's smaller than this one? You know what I mean? Then you have a negative in here, you get imaginary answers. What does that mean physically? Yeah, so think physically about what happened. Like, if I hold it up to here and let it go, there's no friction or no loss of energy. It'll go forever between, the highest it's ever going to get is that angle I released it from. It's never going to swing a little higher than it started. Okay, and so this solution doesn't make any sense for angles of theta that are bigger than capital theta. Who's with me on that? I know Christo is. Any other questions about that one? Okay, and then you wanted to see also 17? Okay. You got a cart on a ramp connected to a spring. We have to calculate how far it's stretched beyond its resting length when it's at rest. And then it's pulled back a little and it oscillates. The angle is 30 degrees. Okay, and here's the cart. It has a mass of 1 kilogram. The spring has a constant of 250 newtons per meter. So first, how far is the spring stretched? And when I talk about stretched, I'm talking about how much longer is the spring than it is when it's just sitting on a table. So past its resting length. At equilibrium. So when it can just sit there and just sit there at rest. Okay, the wording gets a little confusing here because rest sort of means two different things. We talk about the resting length of the spring, which is the length of the spring when it's sitting there. And then we're talking about the length of the spring when this system is at rest. When this system is at rest, that spring is going to be a little longer than it is sitting in a drawer, sitting on a desk, right? Because the weight of the cart is going to stretch it out a little bit. Right, the spring has to apply a little bit of force to keep this system at rest. If the spring wasn't applying a force, that cart would just, roll down the ramp. And if the spring's applying a force, it has to be different than its resting length. The spring applies 0 force at its resting length. All right, well, let's do a free body diagram. of the cart. There's a weight force, a normal force, and then there's a spring force. And for this, I'm going to use a rotated coordinate system like this. Well, the origin of this coordinate system is at the position where the spring is at its rest length. And I'm going to do that so that anytime you have a non-zero x value, it means that the spring is moved away from its resting position. Okay. And so now we have to think about the sign. If the x value is positive, the spring is stretched, you know, the object's moving down the ramp. And so if you stretch the spring, it pulls on the object. And so a positive value of x means that the force is in this direction. So I'm going to write this as, so this is 250x. And think about the other one. If x is negative, the object's moving up the ramp. And so you would get a negative 250, 250 something negative. And so that would switch the sign of this and push it down the ramp. So that's the right sign. Who wants to ask some questions about that? That can be a tricky thing, getting that sign right. So to get the sign right, you just have to think, about what direction that force has to act if the object moves away from the spring's resting length, the positive x direction or the negative x direction. And that tells you the sign of this value. Okay, so now let's go to Newton's second law. The weight force, that would be, what do you get? So it's 1 kilogram, so 9.81 times cosine and sine of 300 degrees. Can you tell me what those are? This one is 4.905. This one is negative, I should remember that one, it comes up a lot, 8.66. No, less than that, 8.4. I know I've seen this a million times.
-8.4957.
Okay, negative 8.4957, so 8.50. Okay, and then that's with the rotated coordinate system. Then we have 0, n, and then we have 250x, but that's acting in the negative x direction, so negative 250x 0. And what's the acceleration? 0, yep. So this gives us that x is equal to 4.905 divided by 250. So what do you get for that? Point 0196. 0196 meters, so like 2 centimeters. It's stretched like 2 centimeters past its resting length. Any questions about that part? Okay, and then it's pulled back 5 centimeters from that position we just found and released. We want an expression for the speed as a function of position. So we didn't use energy on the first part of this problem, but now we're going to, because we're relating a position to a speed. If you look at the free body diagram, what conservative forces do we have? And one more this time. Yep, the weight and the spring force. And then do we have any non-conservative forces? The normal, but that one does no work, so. So we can use conservation of mechanical energy. So we have an instant 1 and an instant 2. What are our 2 instants? What do they represent? What's going on at these 2 instants? I mean, you're always choosing 2 instants where you want to find stuff or where you know stuff. I mean, those are the only 2 reasons you would choose those instants. Yeah, the starting position. So that's when it's stretched 5 centimeters past. Oh, well, so that is the equilibrium position, but the starting position of this, which is what we're going to use, 5 past that, right? Oh, that's what you said? Okay, yeah. I imagined what you said and then answered that. And then what would be our instant 2? That would be just for a general position x, because we're trying to find a relationship between this general position x and the speed. So at instant 1, our potential energy, well, now we have 2 types of potential energy we have to deal with, the gravitational and the spring. What do we want to choose as our 0 position? The easiest thing to do is choose your 0 height to be at the spring's resting length. And that's because then you can use a single variable x to represent the potential energy due to the spring and due to the weight. So h equals 0 is at the spring's resting length. Okay, so if this thing is at an x position of 0.0696, how would we figure out the gravitational potential energy? So if this is, what we want to figure out is we want to figure out the change in the height. And we are at a distance of 0.0696 along the ramp. And we want to break that up into a vertical part and a horizontal part. This angle is 30 degrees. And so the change in height is going to be 0.0696 times the sine of 30. And so that's just 0.0348. Who's with me on that? So the height is negative, since this is our zero height. The height of this thing at its starting point is negative 0.0348. So the gravitational potential energy is the first one we're doing is the gravitational. So we're just trying to figure out, when you pull it back along the ramp 0.0696 meters. Okay, so that relates to the two things that use the word rest. One is the length of the spring sitting on a table, and that's the spring's resting length. And when the spring is at that resting length, that's what we're calling height equals zero. Okay, and then the other one is the whole system is at rest when the object is pulled an extra 5 centimeters from that spring's resting length. So h equals 0 is the spring's resting length, not the system's. Okay. So the gravitational potential energy is negative 9.81 times 0.0348. And now the spring's potential energy is 1/2 times 250 times the distance squared that the spring is stretched past or compressed past its resting length. So this is 0.0696 squared. And then what's the kinetic energy at instant 1? 0, yep. And then at instant 2, what's a representation of the gravitational potential energy? So at instant 2, what x value are we at? Yeah, that's right. So this is equal to negative mg times the sine of 30. Mg should be x times the sine of 30. So this is negative mgx over 2, and mg is 9.81. So this is negative 4.905. And then what's the spring potential energy at this arbitrary x value? Yep, exactly. 1/2 times k times x squared. So that's 125 x squared. And what's the kinetic energy? 1/2 mass times the speed squared. We don't know what that speed is. We're trying to come up with the speed as a function of x. So we'll just leave this as 0.5 v squared. And now you can put this all together. So conservation of mechanical energy. What's 9.81 times 0.0348? Negative 0.03414. And what's the other potential energy at instant 1? This is positive 0.605. Kinetic energy is 0. And all this is equal to negative 4.905x plus 125x squared plus 0.5 v squared. Multiply everything by 2, and you get negative 0.06828 plus 1.210 is equal to negative 9.81x plus 250x squared plus v squared. Can you subtract those two constants? Okay, 1.1417. You got negative 250x squared plus 9.81x plus this. And this is positive, so that's the answer. Any questions about that one? So you're always choosing your two instants based on the instant that you want to know something about and an instant where you know stuff. In this case, the instant we want to, in both of these two problems, the instant we want to know about is this arbitrary instant where things are just defined by x or theta and v. And so we use the instant that we have information about to come up with that expression. Okay, let's take a 10-minute break, come back at 5 minutes to 9, and then, who had a question? Kevin? So we'll, yeah, sure. We'll just keep doing this. So number 13. So you have a skier skiing across a hill, skiing across a flat. That's a hat. And this hill is 5 meters high. The mass is 50 kilograms. And we want to know how fast the skier has to be skiing across the flat for that momentum to carry this person up to the top of the hill. So let's think about what kind of forces there are. Okay, so there's a weight force. And for the first part of the problem, there's only a normal force. There's no friction in part A. And so conservative forces have the weight. Non-conservative, you have the normal. That doesn't do any work. And so we can use conservation of mechanical energy. So what are going to be our two instants? Instant 1 and instant 2. Yeah, so this is at the top. I just spelled top with a 5. This is on the flat. We can choose the flat as our height equals 0. So what's the gravitational potential energy along the flat? 0, yep, 0 height. And kinetic energy? So yeah, what do we know about the speed? Well, we know it's going to be 1/2 times 50. But what do we know about the speed on the flat? That's what we're trying to find here, is the speed as he's going along the flat. So I'm just going to leave that as v squared. And then at the top of the hill, what's the potential energy? So that's mgh. So what's the height? 5. And so that is 24, 25, 22. What's that equal to? 50 times 5 times 9.81. Like that, maybe? 24. I know I've seen this number a million times too. $52.5. 2452.5. And then what's the kinetic energy at the top of the hill? 0. Yep, we're trying to figure out the speed just so he just gets to the top and stops dead right at the top. That's the minimum speed at the bottom. So conservation of mechanical energy says 25 v squared, 0 plus this is equal to 2452.5 plus 0. And so divide everything by 25 and you get v squared is equal to 100. 100g, 981. Is that right? And then so v is equal to square root of 981, which is 11.9? 9.9 meters per second. That's not right, is it? 31.3. Okay. Any questions about that part? Okay, now part B, there is friction. So now friction takes away 400 joules, I think, 400 joules of energy. Okay, so let's think about the free body diagram here. There's the weight down. That is, well, I'll just write it like that. There's still the normal force. And now there's a friction force. And so what are the conservative forces? The weight. Anything else? It's non-conservative because you can think, so do I know the force of friction if the stapler is here? No, because I don't even know whether it's going this way or that way, and that changes the direction. So the only conservative force is weight. Non-conservative forces, we have the normal force and the force of friction. This one does no work, but this one does do work. So here's you. Oh no! Now what? Okay. Now we have to deal with the work done by friction. And so remember that, so the conservation of mechanical energy doesn't really apply. So we have to think about this in terms of the work energy principle. Anyone remember what that says? Total work is equal to the change in kinetic energy. And so you can think of this work as the work done by non-conservative forces minus the change in potential energy, right? Because this is because the work is equal to the negative change in potential energy. And this is equal to the change in kinetic energy. So now we can set it up the same way as we did before with an instant 1 and an instant 2. Calculate the potential energy, calculate the kinetic energy. We can rewrite this like this if you want. You know, the work of the non-conservative forces is equal to the change in the kinetic plus the change in the potential. And we can still set it up as 2 instants and use those to calculate these changes. We just have to include the work done by non-conservative forces now, and that's the work done by friction. Okay, so what's at instant 1, what's the gravitational potential energy? Zero, yep. So we still have our height equals 0 on the flat. What's the kinetic energy? We don't know it. It's just the same as it was before. That's just 1/2 mv squared, so 25v squared. None of these things are going to change from part A. The only thing that's going to change is we have to include the work done by the friction now. What's the gravitational potential energy at the top of the hill? Yeah, 2452.5. That's mgh. And what's the kinetic energy at the top? 0. And so now if we put these together, the change in potential energy is 2452.5 minus 0. The change in kinetic energy is 0 minus 25v squared, so negative 25v squared. And now we can put that into the work energy principle. What's the work done by friction? And be careful of the sign. Friction always takes energy away from things. Friction can't ever add energy. So we have negative 400 is equal to 2452.5 minus 25v squared. And so 25v squared is equal to 2852.5. And so what do you get for v? Either that's wrong or part B was wrong. I don't know which one. Part A. Do this one again. Can someone punch that in? Oh, 98.1. Oh, okay. 98.1. And so this is 9.90, like you said. Sorry. And then this one is what? 10.68 meters per second. Okay, so does it make sense that if the hill, the friction on the hill is stripping energy away as it's going up the hill, you'd have to have a higher speed on the flat to make it to the top? Yeah, that makes sense. So, yes. Well, mathematically that it works out the same way, but is that right? But really, you want to be clear about what all these things mean. I think that's the most important thing to do, you know. And so, potential energy only has to do with conservative forces, and you use those functions for the potential energy to calculate, you know, at each instant. The work done by, you know, friction is a non-conservative force. So there's no such thing as potential energy for friction. And so you want to put that separately into that equation. That's the work done by non-conservative forces. Okay. Any other questions on that one? Okay, and then number 15. A 1/2 kilogram object moves from the point 10 to 410. So it moves from 1, 0 to 4, 10. So from here to here or something. We don't know anything about the path. And it's acted on by three forces: a normal force, a conservative force defined by this function, okay, so what does it say, a normal force? And then a conservative force that follows this function, 5x squared minus 2x. And a second potential energy, a second force field with a potential energy function of negative 6y. And we're trying to figure out the total work. Well, if the only non-conservative force does 0 work, then we can use conservation of mechanical energy. So U1 at instant 1, you can just plug in those x and y. You get 3 for U1. For U2, you get 0. At instant 2, U1, you get, it's 4, right? So 5 times 16, 64, 72. 5 times 16 is 80. 5 times 16. Okay, so 96. Oh, 5 times. Yes, 80. Oh, minus 32. And so that's 48. 4, right. 72. Okay. And then U2, 6 times 10, that's, yep. And so the change in U1 is 72 minus 3, so 69. The change in U2 is negative 60 minus 0, so negative 60. What's the total work done? The work is the negative change in potential energy. So that's negative 69 minus 60. So negative 9 joules. And then what's the change in kinetic energy? Well, the work energy principle says the work is equal to the change in kinetic energy. So the total work is also negative 9 joules, or the negative change in the change in kinetic energy. Any questions about either of those? And then the last one, if it has a speed of 10 meters per second at the start of the motion, I think this is the one that we find out is impossible, but let's, what's the object's speed at the end of the motion? So let's go back to this table. The kinetic energy at the start, it has a mass of 5 kilograms. At the start, it's moving 10 meters per second. So this is 1/2 times 0.5 times 10 squared. So that's 25. At the second instant, it's 1/2 times 0.5 times v squared. So 0.25 v squared. And we can use conservation of mechanical energy. Conservation of mechanical energy says 3 plus 0 plus 25 is equal to 69 minus 60 plus 0.25 v squared. And so 28 minus 9 is 19 is equal to 0.25 v squared. Oh, this is possible. And so 76 is equal to v squared. And so what do you get for v? That's true. 8 point what? So 8.7 meters per second. Mm-hmm. So to do problems like this is the kind of stuff you have to be able to do, and it just takes, you know, going through the notes a lot, going through the problems a lot until like you can make the connections. Like, okay, there's no work done by non-conservative forces, so these tools are available. I can use conservation of mechanical energy. I know that negative change in potential energy is equal to work, and you can always use the work energy principle. And if you, in this case, if you thought of those three things, you could set everything up in this problem. Integrate those two functions to get the Yeah, you can integrate that. So you get, Mm-hmm. Mm-hmm. Okay, let's do it. So we'll integrate. Where are the two functions? 5x squared minus 2x. So integral of 5x squared minus 2x, integrate that with respect to x, and we're going from 1 to 4. And so that's 5 thirds x cubed minus x squared, evaluated from 1 to 4. And that is 64 times 5 over 3. I want to calculate that. 90.6 repeating. And then minus 16. So that was wrong. The whole thing's what? 90 even? Okay. And then the other integral goes from 0 to 10. And what was it equal to? Okay, so the function is negative 6y integrated with respect to y. You get negative 3y squared evaluated from 0 to 10. And what did you get? Negative 300. And that's the work. So the total work is equal to negative 210. Let's see. Oh, yeah, because no, you can't integrate because these are not force functions; they're potential energy functions. That's why. So what I did here makes no sense. I'm going to erase it, and then no one will ever know I even did it. But yes, if those were force functions, not potential energy functions, then you could do it that way. Any other questions about that?